The purpose of any combustion control system is to safely and efficiently maintain the desired boiler output without the need for constant operator attention. Therefore, the combustion process inside the furnace must be controlled while the boiler output changes in response to load demands. The basic principle of combustion control is to meet the boiler load requirements by regulating the quantities of fuel and air while achieving the optimum combustion and maintaining safe conditions for operator and equipment. By the way, this module is based on ANSI ISA 774101-2015, the fossil fuel power plant boiler combustion control, and the NFPA 85 or the Boiler and Combustion Systems Hazards Code. Just to show the basic combustion control strategies. As we say, various combustion control strategies are based on the requirements for safe, efficient, and responsive control of boilers. More sophisticated controls were developed as instrumentation became more reliable and accurate. The common strategies can be divided into two major categories: positioning system and metering system. In positioning system, fuel and air control devices are simultaneously positioned based on energy demand. Each position of fuel control device assumes a corresponding position for the airflow control device. A control station is normally available for the operator to trim the fuel and air ratio. The positioning system is simple and fast responding, but it cannot compensate for varying fuel characteristics, atmospheric conditions, dynamic characteristics of the fuel delivery equipment, or the imbalance of fuel to air ratio during rapid load changes. While metering system measures the actual fuel and air delivered to the boiler. The measured flows are used in feedback control schemes to precisely regulate the fuel to air ratio. And these are the windows in the operator station where we monitor and control the combustion air and furnace drop for units 1 and 2. While this diagram is the original APC diagram for combustion air and furnace drop control. The succeeding slides are the PAG3 APC diagram on combustion air and furnace drop controls. Right here, you can pause the video and take a look and try to interpret. But don't worry if you cannot, since there are a bunch of different function blocks. We will discuss the most important in the next slides. As a basic principle, furnace drop is controlled by the induced drop fan vanes, and airflow is controlled by the forced drop fan inlet vanes. So we can divide the combustion air and furnace drop controls into three subloops, namely furnace drop control, combustion air control, and the FDF inlet vane control. Now, take note of this line signal because this will be significant in our discussion later on. Let us now discuss the combustion air control in a little more details. The oxygen density is measured at the economizer outlet on the left and right sides. The values are summed and divided by 2 to to get the average. This value is now compared to the oxygen bias signal to produce an error signal. The oxygen bias signal is trimmed by comparing the fuel command with the mixed combustion ratio. The error signal is sent through a proportional integral controller to the transfer block. If the permissives are satisfied for auto air-fuel ratio control, the transfer block sends the oxygen density signal to the multiplier block. If the permissives are not satisfied, the transfer block passes the signal from air-fuel ratio setter to the multiplier block. The total demand and total flow signals are sent to a transfer block. The transfer block passes total fuel demand in the light oil control or to the millmasters if they are in auto. If the fuel controls are not in auto, total fuel flow is passed. The output of the transfer block is the fuel command signal. This is summed with the boiler airflow and the resulting value is sent to the multiplier block. The product of the multiplier block is the set point. The set point is now sent to forced draft fan inlet vane control. The set point that we recently discussed from the multiplier block is compared to the actual airflow to create an error signal. The actual airflow signal is achieved by summing the values of the primary air fans and the outlets of the air heaters. The average temperature from the air heater outlet is used to temperature compensate the air heater outlet flow signal. The comparator sends the airflow deviation signal through a PI block. The output of the PI block splits into an alpha and a bravo signal, one for each forced draft fan inlet vane control device or drive. The operator can bias these signals between the two forced draft fans with the forced draft fan bias setter. The signals are sent through transfer block to the forced draft fan inlet vane control drives. If later, a zero signal is substituted through the associated transfer block. And for the furnace draft control, there are a number of features associated with this control, which acts directly onto the induced draft fan vanes on discrepancies between the furnace pressure measured signal and the set point. There is a deadband setting to prevent overshoot of the pressure as well as a necessary response to small transient deviations. There is also a feed-forward signal from the forced draft fan controller, the one that we reiterate earlier, to the induced draft fan controller to ensure steady control. Several features include triple redundant furnace pressure measurement that are compared, and if deviations occur, will trip the control to manual. Directional blocking of the forced draft and induced draft vanes of a high or low pressure occurs. On a master fuel trip, a feed-forward signal are sent to the IDF vanes to decrease to a preset percentage of demand that existed prior to master fuel trip. When the preset level is reached, the pressure control will reset to automatic. The actual furnace draft is compared against the set point from the furnace draft setter. The error signal or the furnace draft deviation is sent to a proportional integral block. The output of that PI block is trimmed by the inlet vane positions of the forced draft fans. The operator can bias these signals between the two ID fans with the ID fan bias setter. The signals are sent to the respective induced draft fan inlet vane controls from there to the drives. And again, I would say that if you want to study or understand how control logic works or how control systems was implemented, use Sama diagram. But if you want to see, understand, or interpret what's happening in the plant or with the control system in real time, you should use signal diagram or logic diagram or control sheets. And it is easier to analyze in real time if you know how control systems was implemented. Kaya kahit paikot-ikutin man kayo sa pag-trace ng signal diagram, hindi kayo mahihilo. Now, when it comes to interpreting the control sheets or signal diagram, you can refer to the previous module on interpreting signal diagram. Let us analyze this control sheet. Look at the lower right corner. It is entitled FD inlet vanes. The problem with this is that there are a number of control sheets na text algorithm lang ang title, or something that is hard to relate with the content. Other info is that it is on task 3 of drop 3 and numbered 088. Okay, we have the analog inputs at the top, analog outputs at the bottom. Another dilemma is that most of the input or output are not labeled. So you have to trace saan to nanggaling for you to have an idea of what it is. Pero yung mga pamilyar na sa control sheets, alam na nila agad pagtingin pa lang sa title or sheet number. Digital inputs on the left, PID controller, several transfer blocks and mass stations. Trainings like this, or even face-to-face trainings, doesn't work like a magic wand, a genie, or a talisman with abracadabra. Knowledge and skills are acquired through experience, hard work, perseverance, and proper mindset. I included here some references if you want to follow through. And if time and circumstances will permit, you will be able to practice reading logic diagrams in our simulator. That's all for combustion and furnace draft control. Please continue on the next module.